So unit 2 is about application of operational amplifiers, where you will come across integrator, differentiator, analog digital converter, Schmitt trigger, and other sort of wave shaping circuits, and also the 555 timer IC. So today we'll start with the integrator. So before starting, please, whenever you see any calculation, please pause the video and do it by pen and verify the values. The slides which I am going to use are taken from All About Circuits website. So we have seen this inverting op amp, and I hope that you guys are still remembering this stuff. So this is inverting op amp. You have written your midterm exam on this particular schematic of operational amplifier. So if you want to convert this into an integrator, you have to just remove this feedback resistance, which is RF, with the capacitor. So here in this circuit you are seeing a capacitor is connected in place of feedback resistor. So I input current is flowing through resistor R, and then IC current is flowing through capacitor and then reaching to the output side. So here the yellow circle which you are seeing just beneath the IC current can be taken as virtual ground, so its potential will be 0, and then we can apply our KCL for the circuit analysis. So if we try to write equation for try to write KCL for this particular point O, we will write I in is equals to IC. So I in value will be V in minus 0 by R, which should be equal to IC. For finding out IC value, you have already seen several times. This is current across the capacitor, which can be calculated by IC is equals to C dVc by dt. So this IC value we can equate in our previous equation. I in is equals to IC. So V in by R can be written as CF dVc by dt. On rearranging this equation and then on integration on both these sides, we will get this V out is equals to V out of t. Please mind, because this is indefinite integral. So V out t is equals to minus 1 upon R CF. Integrating V in of t dt. So this RCF value is the rate of change of the output. So when you put any input value in this integration, so the result you will get in the form of V out. So these are a few examples. For example, on the left hand side upper corner, you are seeing a sine wave. When you integrate a sine wave, you will get a cosine wave. On the right hand upper corner, you are seeing a square wave, which when we integrate, we get a triangular wave. So let's analyze this integrator using op amp. So we can write the overall gain of this operational amplifier as minus XC by R. So if you observe the formula for AV, so for F is equals to 0, it means when your operating frequency is 0, at that time AV should be infinite, which is for the ideal case. But practically F can be very small, so then AV value will be very high. How much high? It is approx 10 to the power 6 or 10 to the power 5, in between 10 to the power 5 and 10 to the power 6. So this same analysis, this same frequency analysis, you can do using your Laplace transform. If you have come across Bode plot in your control system, same steps you can follow for analyzing the frequency response of this particular device. So what you will observe? You will observe this sort of frequency plot. So this is the plot between gain and the frequency. So when we increase frequency, the gain is coming down to 0. So which means if F is tending to infinite, if you put in this formula of AV, what you will see? AV is becoming 0. And same with when F is very small, it is reaching 100 dBs. 100 dB is nothing, 10 to the power 6 overall gain. But when F is 0, what happens with this circuit? When F is equals to 0, then we are talking about the DC analysis. when we do the DC analysis, our capacitor will act as open circuit. And when it is acting as open circuit, which means there is no particular feedback path for this circuit, then the overall gain will be nothing but the open loop gain for this integrator or the op-amp. So we have to be very careful here, which means open loop gain ideally we have seen is very high, which is 10 to the power 6. So when you are operating with this for small signals of very low frequencies, from where these small signals will come? Due to the offset. You know, there is no practical op-amp as such. All op-amps will have some offset. If this value is in millivolts, still this will create lot of distortion in the circuit. So to avoid this problem, we will come across practical integrator using operational amplifier. So for making this practical integrator, you have to just connect a feedback resistor in parallel with the capacitor. So what is the advantage of this particular thing? While doing this, if you observe, if we operate frequency f is equals to 0, then this gain, open loop gain, will become AV is equals to minus RF by R1. So we are able to avoid that open loop gain of 10 to the power 6 value, because when we operate with low frequencies, still this CF is open circuit, still you will be able to see a path which can complete this whole circuit. So it is suggested that we should always connect a feedback resistor across capacitor for making practical integrator. In same manner, for balancing the bias currents, you can connect a resistor in the non-inverting terminal of the op-amp. So what happens to the frequency response? So here you see the yellow line. The yellow line is representing the frequency response for the practical integrator. So when it is operating on low frequencies, the gain will be RF by R1. And then it will, when it crosses a certain lower frequency, FL value, it will die down as it was doing for the ideal integrator. So FL value you can always calculate as FL is equals to 1 upon 2 pi RF CF. So in later stage you will observe that these same integrator can also be used as filters. So it is nothing but low pass filter. So but today we are discussing it as integrator. So why these values I am showing you? Because FL suggests us, if you want integration from any op-amp, then the input signal frequency should be 10 times of this FL. Which FL? Which you will be able to calculate by the values of RF and CF. And F naught is equals to 1 upon 2F RCF. F naught is the final frequency. When you go beyond FL, there will be frequency where you will be able to see gain as 0. So this F naught is representing that particular frequency. So from this point we can conclude, and you can take note also, if you want your integration operation to take place, then the input signal frequency should lie between this FL and F naught range. Now we will try to understand this with the few examples. This is the circuit. So you have to find out the lower frequency limit for integration. Lower frequency limit for integration simply means the minimum frequency beyond which you will be able to see the integration taking place by this particular operational amplifier. So as the formula suggests, FL is equals to 1 upon 2 pi RF CF. So what is the value of RF here? 100K. CF is 10 nanofarad. So when you put this in the formula, so FL is equals to 159 Hertz. So your signal frequency should be 10 times of this FL frequency. Now let's take the second example, and by the way, you guys are encouraged to calculate all these things by using pen and paper. So now we change this same question by applying a sinusoidal input. So in this sinusoidal input, which is Vin is equals to sine 2 pi 5000 t. So 5000 t, if you compare with 2 pi omega t, so omega is 5000. It means 5 kilohertz. So what is our basic condition? That our signal frequency should be 10 times greater than FL. So let's check. So we have already calculated. FL was coming 159 Hertz. So 10 times it is 1.59 1.59 Hertz. So 10 times FL means 1.59 kilohertz. So the basic criteria is satisfied here. This is 5 kilohertz, which is definitely greater than 10 times of FL. So we are good to go. So now let's find out V out value. V out value by the formula which we have derived in the very beginning. V out is equals to minus RCF integral V in t dt. So put all these value. R value is known to you, 1 kilo ohm. CF value is 10 nanofarad. Put these values and calculate. V out will come out as 3.18 cos 2 pi 5000 t. So you have to carefully observe the output. So output frequency is not changing, which suggests the shape of the original wave is not gonna change. What is gonna change? The final amplitude. So the swing which was there as 1 volt,
let's take
now that
one
swing
more
will
example.
become
So in the previous
3.18
example,
cos
you
2
have
pi
been given a sine wave
5000
which was
t.
given to the same circuit which you are seeing on the screen. So here again RF value is 100k, CF value is 10 nanofarad, R value is 1k, but the input signal is square wave. So we have seen previously in the class how to deal with this square waves. So square waves can be first of all, before jumping onto the solution, we have to check the basic condition for integration. So here you are seeing a square wave having time period of 100 microseconds. So what is the frequency of this signal? So frequency of the signal is 1 upon 100 microsecond, which is nothing but 10 kilohertz. So 10 kilohertz is way beyond than the 10 FL criteria. So FL was 1.59 kilohertz. You can refer the last example. So 10 kilohertz is way greater than this. So we can use this signal for getting the integrated output. So we have to divide this square wave in two parts. One is from 0 to 50 microseconds, and then second portion is 50 microseconds to 100 microseconds. You have to write this thing in a form of inequality. So V1t, where amplitude is 2 volts, for 0 to t, where t is between 0 to 50 volts, 50 microseconds, and V2t is minus 2 volts amplitude for t between 50 to 100 microseconds. So if we calculate V out 1 by the formula which we derived in the very beginning, minus 1 upon RCF integral V1 of t dt. So this will give you minus 10 to the power 5 multiplied by 50 microseconds multiplied by 2. So what is the final answer? Final answer will be minus 10 volts. So minus 10 volts is not the amplitude. This is the whole swing of the output wave. Swing means peak to peak. Okay. So your output will look like this. So if you see here, 5 volt to minus 5 volt, it is 10 volts. Okay. So your waveform will start triangular waveform, the slope you will see from 5 volts and will go up to minus 5 volts. So the second part of VO2, I would encourage you to calculate on your own, that you will see again having the same swing but in the opposite direction. So in the output here you will see a positive sign which will represent nothing but the positive slope. So I hope with these examples you will get some clarity about operating with integrators. So in case you have any doubt, please feel free to write to me, and I'll soon share some of the practice questions related to this topic. Thank you.